Okay, let's look at this problem here. We have a circuit with a bunch of inductors on it, and we're told to find the equivalent inductance at terminals AB of the circuit. So we want to figure out what the equivalent across these terminals are. Again, the first thing we want to note is we want to note the characteristics of inductors when they are in series as well as in parallel. So in series, the inductors essentially act like resistors. So our L equivalent is going to equal to L1 plus L2 plus however many resistors we have. And in parallel, again, they're going to act like resistors. L equivalent is going to be L1 times L2 over L1 plus L2. Or if we have more than one inductor, we can rewrite this as 1 over L equivalent is equal to 1 over L1 plus 1 over L2 plus 1 over L3 1 over Ln. In this case, we see that we have 1, 2, 3 inductors in parallel there, so we can go ahead and use that second part of this equation here to add those 3 inductors together. Okay, so again, that's the key here, is to remember that we have these relationships when it comes to inductors, capacitors, as well as resistors. Okay, so let's go ahead and combine these three inductors here, 60 millihenries, 20, and 30, using the parallel equation. So 1 over L equivalent is going to be 1 over, let's say we have 60 millihenries plus 1 over 20 plus 1 over 30 millihenries. We can work this out. We can multiply to get a common denominator. We can rewrite this as 1 over 60 plus 1 over 3 over 60, where I multiply both the denominator and the numerator by 3. In this case, 2 over 60, where I multiply by 2 over 2. And then that's going to give us 6 over 60. And if we simplify that, that gives us 1 over 10 as our L equivalent, or 1 over L equivalent is 1 over 10, which really comes out to be as L equivalent is equal to 10 millihenries. Okay, so we got one part of that there. So across these guys here, if we combine those 3, we get 10 millihenries. Okay, so next we see that we can combine this 25 millihenries with this equivalent that we just came up with, because they're in series, and simply just adding them together. Okay, so we can so the first part of it was taking these guys that were in parallel, and then the second part, we're going to take 25 plus 10 because they're in series. Okay, and we're just going to add them, so that's going to give us 35 millihenries. Okay, so that 35 millihenries, I'm going to write that here. So the combination of this guy and this guy is going to give us 35 millihenries. And then finally, we're going to combine this new 35 millihenries with the 10 millihenries, and those guys are going to be in parallel. So we're going to say, let me go ahead and highlight these guys are and then we got 10 millihenries and 35 millihenries are in parallel. Okay, so let's highlight those. Okay, because they're in parallel, so our L equivalent, so I'm going to write, oops, I'm going to write L equivalent here, and then for this guy our L equivalent is going to be 10 times 35 over 10 plus 35. Okay, and if we compute that, we're going to get 7.778 millihenries. Okay, and that's going to be our final answer. So our L equivalent for this circuit is going to be 7.778 millihenries. Okay, and again, it's just a matter of taking it step by step and working our way backwards by combining series and parallel patterns using the characteristics of inductors. Okay.